Let's discuss work, which is our last of the applications of the definite integral, and it's quite a fun section. Before we get into work, I want to discuss some equations that come up from physics. And the first is work is force times distance. That force is mass times acceleration. And one we have seen is that mass is density times volume. Now, if this was all there was to the story, we wouldn't be studying this in calculus. So what I need to add is that these hold when you're in the constant situation, and moreover, for the first equation, you need that the force is parallel to the distance that's traveled. Like this, okay. Then you just multiply all these quantities. And the calculus comes into play when things are not all constant. As we have seen even with this bottom equation, that was when we were calculating mass, when we had variable density, for example, became an integral. And we will see this with work. Before I get to that, so there's one more thing I want to discuss, then we will get into the work calculations. And what I want to discuss is units. In this section with work, we want to discuss both U.S. customary and metric. You might recall it when we did mass and density, we really only worked metric, but we also will be working U.S. customary, and we need to feel comfortable going back and forth, or not so much. Okay, it's focused. We need to be comfortable in both, I should say. That we should feel comfortable working U.S. customary, we should feel comfortable working in metric. Okay, well, U.S. customary is a bit easier, and I'm going to start way down here and just talk about the force, and then the distance, and then force times distance gives us work. The units of force in U.S. customary is the pound, and this, many of you will be used to thinking about. This is a force. This is if you step on the scale and you read what it says, however many pounds, this is a force. Okay, the distance is in feet. And work, well, force times distance, it's called foot-pounds. So this is foot-pounds. Well, maybe I should keep the same thing where first I write it in the word and then in the symbol, this is foot-pounds. And it is denoted exactly as it sounds, foot-pounds. Okay, so this, in a sense, I think U.S. customary is a little bit easier than metric. Metric, we have to back up a little bit because you might have, either if you are from another country or if you have traveled to another country, you might have thought about your weight in kilograms, but it's not exactly, you can't compare kilograms to pounds, not really. When you see the conversions between the two, it's really because of the gravity on Earth. Kilograms is not a force, but in the metric system, it is up here. This is a mass, as we saw with our mass and density. So in the metric system, the mass here is kilograms. And then, if you look at these equations, to get a force, you need mass times acceleration. The acceleration is typically due to gravity, and this is what, the multipliers that go back and forth between these two have that factored in, as I was mentioning, but acceleration is in, it would be in meters per second squared. This is the acceleration, and you can even think about this from Calc 1, for example, of why these units would be right, because your location is in meters. Take the derivative, velocity, that would be meters per second. Take the derivative again, acceleration, that would be meters per second, or meters per second squared. Now we multiply, now we're ready to talk about the units of force. Maybe I'll put a line here because these two came up in the metric. The units of force here, well, we just multiply. It is, but it has a name. It's a Newton. And it's denoted capital N, but this is kilogram meters per second squared, okay? This is the unit of force in the metric system. And then distance is meters, as we know. M. And the unit of work, one way to say it is a Newton meter. Newton meter, which is Nm. Or there's a word for it, which is joules. So the unit of work in the metric system is a joule, which is 1 Newton meter. Okay, so it's important that we have this down, because when we're setting up problems, maybe I will stand here, when we're setting up problems in work, checking our units, checking we have all the pieces will tell us if it's set up right, or at least it'll tell us if we've left something out or not. So it's good to have an understanding of the units. Okay, so we want to now move into the calculus, which involves, well, the things I'm erasing now. You have things that are not constant anymore, right? And just like we did with density and mass, instead of multiplying, we will be integrating. But there's a little more setup to it than there was in density and mass. And in my opinion, it makes the problems in this section much more interesting. Okay, so when you're in the not constant case, when not, I'll say all quantities are constant, this is where calculus comes in. So we have two ways to find work. And these are my two ways that I go about it. And I will mention the two ways and mention what types of problems that I do in each way. And then we'll go and see some examples. The first way that is called slicing. And what types of problems do I slice? Well, lifting a rope, I slice. Pumping water, I slice. And then the second way is by scooting. So some work problems I slice, some work problems I scoot. And I'm trying to give you my personal, which way I go about which one. For scooting, I scoot when it's a spring. I scoot when it's a leaky bucket. And I scoot for general variable force. Okay? This is as I mentioned, this is my personal way that I do them. And these are the types of different work problems I have. So let's start with slicing. We will do lifting a rope. We'll do a few examples of pumping water because it's a little bit more intricate. And then we will move on and do some scooting. Okay, so let's do our first example. So we have a rope and it lies over a very tall building. Okay, and the rope is 50 feet long and weighs 2 pounds per foot. Okay, and we want to find the total work. So immediately we know we are US customary, right? Because we see feet and pounds. We want to find the work to pull the rope or lift the rope to the top of the building. Okay, so let us first draw a picture and then we will discuss, while it's lifting a rope, we are slicing. Okay, my picture is something like this. It's a very tall building. And it doesn't really matter the height. I could have put a height of the building in the problem, but by very tall, I just mean it's more than 50 feet. So it's taller than the length of the rope. Okay, here's my building. And then my rope is, say here, and then it goes down maybe to here. And the rope is 50 feet, okay? Now I will also just start labeling things. I will put an axis in my picture and label it, and I will typically always label what makes sense. So for instance, this is a vertical thing, the rope, so I'm going to label it with Y's. If I had something horizontal, I would label it with X's. To me, that just keeps me sane throughout the process. So this is going to be 0, and the top here, this will be 50. Okay? And I want to find the total work. Now, to lift it up, right? So this is going to be lifted up to here. Now, well, the whole rope, I should say. The whole rope gets lifted to the very top. But it is not just force times distance. That would be a different picture. So if you could think here, what's our force? Well, we have 50 feet long times 2 pounds per foot. My whole rope definitely weighs 100 pounds, right? But it's not just 100 pounds times 50 feet. That would be the wrong picture. What that would be is you have a rope like this, okay, and it weighs 100 pounds, and then you lift it up. Well, if this is 50 feet, we lift the whole thing up 50 feet. So the bottom is now here, like this. So in this picture, I am showing lifting 50 feet. But every single location on the rope all goes 50 feet up in the air. And in this picture, we would have, well, we have 100 pounds times 50 feet. This is in pounds. This is in feet. We would have 5,000 foot-pounds. Right? But I'm mentioning this to mention that this is a valid calculation, but it's the wrong problem. Our problem is different because, for example, okay, it goes here. If you're maybe 10 feet down, you do not travel 50 feet. You travel just those 10 to get to the top. If you're all the way down at the very bottom, then you travel 50 feet. But if you're halfway in between, like this piece of the rope, which is 25 feet in the middle, it's only traveling 25 feet, to get to the top. So we do not have the entire rope moving 50 feet up. This is not the right calculation for this problem, okay? So we cannot just multiply force times distance here. So this is when we slice. Okay, now, you could do this in a remind sum. In fact, that's the setup where I would subdivide 0 to 50 into n subintervals that are very, very, very small. And then I only think about moving each subinterval, right? But instead of setting up the whole remind sum, which I've done in multiple videos now, let's just think about one slice and then convert to an interval. So if I slice, so I make a little slice here. And this is of thickness delta y, because this is all vertical. And here on my axis is some little y, right? All I'm going to think about at the moment is the work to move this little slice. We're slicing this little slice of rope to the top, okay? And it's subdivided so fine that everything in this little slice moves about the same distance, right? So the work for the slice, the work to move the slice to the top, well, we need force times distance. So we have 2 pounds per foot times, well, how long is my slice? It is the length delta y. So this is delta y feet, okay? And I'll put my units underneath so we see here. This is in pounds per foot. This is in delta y feet. So far we have our force, it's in pounds. Then we must think the distance that this slice travels to the top, right? Well, if this is 50 and this is y, this will travel 50 minus y, okay? So then 50 minus y. This is now I left off my t. This is in feet. And you notice, this is what I meant about checking my units. I have work because this is pounds, this is feet, we have foot-pounds, okay? So we have a work. Okay, well, we could add them up over all the slices, and this would approximate the total work. Then, as you know, we can take a limit as delta y goes to 0, or equivalently as n, the number of slices, goes to infinity. But once we have this, we can set up the integral. So the work, total work, is equal to, it's the integral. Well, my slices range between 0 and 50, 0 to 50, and then here is the function I'm integrating. The delta y becomes the dy, right? So we have 250 minus y dy. Now let's integrate. This is not too terribly bad to integrate. This becomes 100y minus y squared from 0 to 50. So we get 5,000 minus 2,500. We have 2,500 foot-pounds. Okay, so this is the total work in this example. And it was our first example of slicing. What I'd like to do now is let's move in and do some with pumping water. The pumping water problems, well, the rope is kind of a warm-up in a way because it wasn't too terribly difficult. The pumping water problems are a little bit more involved, and so I'm going to do more than one of those. These I will maybe just set up. Okay, so example, let's suppose we have a tank is in the shape of a right cylinder. I'll say circular cylinder. Okay, with radius 5 meters and height 12 meters. Okay, and then let's suppose the tank is 3/4 full of water. Okay, and then the question is, how much work is it to pump all of the water out of the top of the tank? How much work to pump or I'll say is required to pump all of the water out of the tank. Question mark. Okay, now one thing that I need to tell you, well, first of all, you see we have meters in this, so we are in the metric system, but I also need to tell you about the density of water. The density of water, we can use this, is as 1,000, let's say, kilogram per meter cubed. Okay, so we can use this in our, and we will just set this up. We will set up only. This is the hard part of this section. Hard meaning new, okay, because the integrals that we see are not too bad to calculate, as you will see when we have it all set up. Okay, let's draw a picture. So I have a right cylinder, or circular, tank. It looks something like this. Okay, and it has a height 12. So I'm going to start labeling things. Here is my 0. I'll just put it at the bottom. And then my height up here is 12 high. Okay? And then my radius here, from here to here, this is 5. And what else do I know? It's not filled all the way to the top. Okay, maybe I should make this a little bit more in the back. Okay, it's not filled all the way to the top. It's 3/4 full. 3/4 of 12 is 9. So we are filled with water to 9 feet. There'd be half, there'd be like this. So here is 9. And I will color in my water with blue. Wonderful. My water is to here. All of this is my water up to 9 feet. Now is when my picture is starting to fall apart. But you have the idea. Maybe I should draw this in green. Okay, this is in the back, like this, in the front. You have the idea. This is my tank. Now, what I need to do is pump all this water out of the top. So, while I'm slicing, I always slice with pumping water problems and rope problems. So, what would happen? Well, I take and I slice it here. This is a little thickness. Comes around the back, a thickness here, delta y. And what I want to do is calculate the work for just this slice. And that will allow me to set up the integral. Okay, here we go. The work for this slice, maybe I should outline it in black because it's a little bit hard to see. I have this slice of water here, which is at some height, say, well, maybe I'll put the delta y on the other side. Here's a y on the y-axis, and then the thickness of my slice is over here, delta y, okay? So the work for the slice, and that is basically most of the problem, and then we just have to set up the integral with the appropriate limits of integration. The work for the slice. Okay, well, this is when you have to go back to all those equations I reminded you of at the beginning, because we don't see a force here, right? We have density, and what else do we have? We know the shape. So we have to go back and remember, if we take density times, I'll back it up just a little bit. Density times, I'll write it underneath, the density of water times volume. This would give us a mass, right? And the volume, this is where we have to use, and drawing a picture is very good. Here, this is, well, it's kind of like a disc with our discs and washers, but it's just a pi r squared times delta y, right, where the radius is 5. So the volume of this slice is, it's pi times 5 squared, pi r squared, times delta y, okay? This gives me a mass. In fact, maybe I'll write my units above. These in particular, I always check my units to make sure I have everything. So this is in kilograms per meters cubed. This is in meters cubed. So far I multiply, I have a kilograms, which is a mass. Wonderful. But then mass, I need acceleration. Well, the acceleration here is due to gravity, which is 9.8 meters per second squared. So we have a 9.8. This is acceleration. So far, this gives me a mass times acceleration. Okay. And this is in meters. Uh-oh, this was supposed to be in red. My units above, I have meters per second squared. And you see, what do I have so far? I have a force, because this is kilogram meters per second squared. All of this together is a Newton. And the last thing I need, because here, maybe I'll even add this, going to here, this is a force. The last thing I need is the distance. And this is very much like we did in the rope problem. If you are here at height y and you're a very thin little slice, this will travel 12 minus y, right? It travels this length, 12 minus y. So the last thing to add here is 12 minus y, and this is in meters, okay? Or if I write it below in blue, this is my distance, and force times distance, this is a work. Or if you check your units, which is always a good decision because we have so many quantities in here, the units, right, this is kilograms, then we add this, kilogram meters per second squared, we are newtons, then we're Newton meters, which is joules. So we have the right units here. This is the work for this slice. And just by calculating this, we can set up the correct integral. So first, let me just write the integral sign, and I will translate all of this. It would be 12 minus y. It'd be 9.8. It'd be 1,000, excuse me. It would be a pi 25 dy. Okay, of course, you could multiply all those numbers. And this is one of the reasons I said that the setup is what's new, or what might seem hard when you first start. Because what all this is one big constant times just some linear thing, okay? It's not hard to integrate. But what we're trying to do is set it up, because that is what's new. Now, the thing we have to be careful with in this problem, you do not want to integrate 0 to 12. That's not this problem. If you integrate 0 to 12, that would be a completely full tank. And ours is not. Here. Okay? You have to think these limits of integration, and this is why labeling your picture is so important. The limits of integration are where these slices may live. My slices can live between 0 and 9. Or equivalently, my water is between 0 and 9. Okay? So you only want to integrate where the water is. 0 to 9. The fact that you're traveling all the way up to height 12, that's already taken effect in this 12 minus y. So you don't need to put 12 here. In fact, if you go all the way up to 12, as I mentioned, it's like if the water was all the way to the top of the tank. It's not, okay? So you just integrate 0 to 9. This is how the limits of integration work. Okay, well, this is our answer here. This integral calculates the total work and would be in joules, right, which we verified thinking about the slice. Let's change the problem just slightly, but it's going to make it more involved and a little bit more, we're working up in the complexity of the problems that we do. Well, maybe I should have left the density of water there because I'm still going to use that. So how am I going to change this? So I'm going to change this. I'm going to change this to a circular cone. Oops. Radius 5 and height 12. And it's going to be full of water this time. Full of water. And then I also need to say that, inverted. Maybe I should erase this, because if you have a circular cone, and you can practice this either in homework or the worksheets I will post, it either sits on the big base part with the tip at the top, or it's inverted with the tip at the bottom and going up like this. So we will do inverted circular cone. With, okay, now this looks good. Radius 5, height 12, full of water. How much work is required to pump the water out of the tank? And I should have left this at the density of water. This is not changed. It's 1,000 kilograms per meter cubed. Okay, now let me draw the picture of this cone. It's inverted. So up here is the circle, and down here is the tip. And it's a right, even though I erased that part, meaning it doesn't sit on its side, it makes a right angle here. So this is still 5. And I can still label my axes. I'll just draw here. Here's 0, and the height is still 12, right? And then this is right. So if you draw a line here, it makes a right angle like this. So it sits straight up. Okay, here we go. Now, what's also changed, it's fully full of water. So the water comes all the way up to the top, okay? Maybe I won't shade it in to confuse the picture. Well, this is a little bit exciting. So we think about slicing. We slice. Okay, and then we have a little delta y here. And this is at some height y. But we don't know, right? What makes this more challenging is the volume of this, because the radius of these slices is changing as y varies from 0 to 12. But you see, this is something that we can handle, and this goes back to, I want to say, maybe you learned this in high school geometry or something like this. I will draw this, and I mentioned this is a right circular cone, so that this here is a right angle. But what's important for us, this is also a right angle, is that if you look at the big triangle and you look at this little triangle here, which is, I will fully outline in green, they are similar triangles. So let me just draw this picture, maybe below, not sitting inside the cone. we have these similar triangles like this, and sitting inside of it is like this. And this length is 5. This big length is 12. And what else do we know? Okay, this is at height y, so this length here, I'll do this one in blue maybe. This length is y, and we're trying to, y, okay, good. We're trying to find the radius here, r. Well, in terms of y, right, because I'm going to be integrating, we have a delta y, integrating with respect to y. I want to find the radius as a function of y because it will come up in the volume of this slice. Pi r squared delta y. I need r in terms of y, right? Okay, similar triangles. Fabulous. Similar triangles says that this ratio, so we have 5 over 12 equals the same ratio on this smaller triangle, r over y. Okay, now we see we're trying to solve for the radius in terms of y. Okay, we have 5y, 12 radius is 5y, or finally we see that we're trying to solve for r, divide. R equals 5 over 12 y, like this. Okay, so this is a formula for my radius. And now this is the big part of the change. Besides the fact that we're fully full of water, the big change was our radius was not constant like it was when we had the cylinder. Okay, so let's calculate the volume, not volume, the work of the slice. We need the volume of the slice as well, but let's do the whole work and then we'll set up the integral. Again, we will set up this. Set up only, and you can integrate this if you like, or you can put it in your software or fancy calculator or something like this to actually integrate it if you want the actual number. Okay, well, let's start back exactly as we did. We need density times volume. Density times, now the volume here is still pi r squared delta y, but here is our radius. So we have pi 5 over 12 y squared delta y. And again, this is density times volume. This is a mass. Maybe I will just write that here. So far we have kilograms. All of this here is kilograms. It's kilograms here per meters cubed times meters cubed. We have kilograms. Okay, and now density times, we have a mass. Now we need acceleration due to gravity. This is the same. Okay, this is in, acceleration is in meters per second squared. So far we have a Newton. We have kilogram, meters per second squared, newtons. This is a force. And finally, we need a distance, which, just like in the last one, this slice travels 12 minus y. Okay? Well, this is the work for this slice. And now we can write our general work as an integral. It's an integral. And I just write all of this in its corresponding integral form, which is 12 minus y, 9.8. Oops, that's a point, not a times. 1,000. We have, well, we could say pi and then what? 25 y squared over 144. If you want to square that, or I could have just left it as it was. It's fine. And still, this would all be just polynomial to integrate, right? We have all this constant, and then we have a y squared and a 12 minus y multiplied. It's not too terribly bad of an integral. The numbers might not be the nicest because of all these constants. Finally, and this is the second part that's different besides this radius calculation, it's full of water. And so I'm integrating the entire 0 to 12 because the water comes all the way up to the top. Okay, so this is an integral here that calculates the total work, and this integral, or this number, would be in joules. Now let's discuss the scooting side of work, and let's begin with variable force. So suppose we have a force f of x, and this acts to move an object from x equals a to x equals b. Okay? This is our variable force. Okay. Now, this is going to be my scooting. Well, let's think about, we subdivide, and this time I will do it. I talked about it in the slicing, but I will actually do it here. Let's subdivide the interval into n subintervals of length delta x, which is b minus a over n. And we take n so large so that the force, such that the force f of x is approximately a constant on each subinterval. Okay, this is what I mean by scooting. Well, maybe you'll see it in a second. Okay, so if you want the work to move, oh, let's see. I should also just have my notation. Okay, we have this partition A, which is x0 less than x1 less than x2, all the way out to xn, which is b, okay? So the work to move this object from xi minus 1 to xi, okay? This is what I think about, you scoot it just a little bit, a delta x at a time, you scoot. Well, the force is approximately constant on this subinterval, and so the work to move this is approximately, it's, let's say, f of xi times delta x. This is a force, and this is, excuse me, this is a distance. So this is a force here, and this is a distance. And it's subdivided so much that the force is approximately constant. This is the scooting. I'll do it again. You scoot it by a delta x. You scoot by a delta x, etc. One little delta x at a time. And then, as you could imagine, the total work is then approximately, you add them all up, a sum, I equals 1 to n, f of xi, delta x, or, well, we take a limit. We've seen this multiple times by now that we can calculate the work by integrating over a to b. This is where the object's traveling, f of x dx. And this is variable force. This is really what I think about in scooting. It's a different notion. You see, I'm not slicing, I'm scooting. And so now let's do some problems where I'm thinking about scooting. And the first one we will do a leaky bucket. Now let's do one of the examples that I said I always scoot, which is a leaky bucket. Now, let's read this carefully. So the bucket itself weighs 2 pounds, and it's filled with 30 pounds of water, and we're going to lift this bucket 100 feet in the air. Then the bucket loses water at a constant rate. And when we are 100 feet in the air, the bucket has only 25 pounds of water left. We want to know how much work is done lifting this bucket the 100 feet. Now, I will say also, we are ignoring, let's say you lift it with a rope, we're ignoring the weight of the rope. Or if there's some other system that lifts it, we're ignoring that for this. You can think about the rope being of negligible weight, for example. Okay, well, first let's draw a picture. Maybe here is my bucket. And here is 0, and I'm just going to lift it up to here at 100. Okay? Lift the bucket, but it's losing water at a constant rate. What happens here is that our force, or the weight, is variable because it's changing over time. Now, well, let's figure out the force function, okay? And then we will integrate it. Okay. Well, what is my force function? Variable force. Okay, let's figure this out. Well, you notice immediately I'm in US customary, and my initial force is 2 for the bucket plus 30 for the water. So initially, when I'm at the bottom, I have 32 pounds. And then when I get to the top, so at y equals 100, I have, 25 pounds of the water, 2 pounds for the bucket, so I have 27 pounds. And maybe instead of writing initially, I will write at y equals 0, because this is what I am. Now, you could think about this as changing over time. I am thinking about this as changing over height. And I will change this slightly in the next one where we have to think a little bit about time. But with losing water at a constant rate, we can write the force function as a linear function, and we want it to be a function of y, our height. So here, as we move from 0 to 100, the variable here is y, okay? Just because I'm using a vertical axis is why I choose y. Well, my rate over the course of, we have 5 pounds we lose, right? And over 100 feet. So we have 5 pounds per 100 feet. This is a negative. This would be the rate. I'm thinking about this constant rate, thinking a line here. And this is negative 1 over 20. And so I can write my force function as, well, you think like the slope intercept, right? When y equals 0, we are 32. And then here is my slope, y, like this. This is my function for variable force, and you could check when y is 0, that's this height, we have 32 pounds, very nice. When y is 100, that's this height, we have 27 pounds. So this is my force function. And then I just integrate. So I integrate, I need to go all the way to 100. And I have 32 minus 1 over 20y dy. Okay, this is just 32y minus 1 over 40 y squared, evaluated between 0 and 100, all of this, which is 3,200 minus, we're going to have what? 1, 2, 3, 4. I think that's right. Over 40. Okay. So it's going to be 3,200 divided by, or minus, excuse me, 250. Okay, this is okay. I was worried when I saw those zeros that I was going to get a negative number. But this is good because this 0 and that 0 cancel. 3,200 minus 250. We have 2950, and this would be in foot-pounds, which is our unit of work in the U.S. customary. Okay, so this is the work here. Now, just like when we were slicing and we did pumping water, I changed it slightly, made it a little bit more challenging. We had to just think a little bit more, and that's what I'm going to do here. So how am I going to change this slightly? Okay, the first sentence is going to stay the same. This part is going to change. Okay, so let's change this slightly where we have to think about time. Okay, it's not going to be the same problem, but it's going to be very similar, and I'm trying to purposefully do a similar one so you see how the setup changes. Okay, so the bucket loses water at a constant rate of, let's say, 0.2 pounds per second, and is lifted at a constant rate of maybe 2 feet per second, and we still have 30 pounds, 2 pounds, 100 feet. Okay, but you see now both of these depend on time. And but I'm going to wind up doing the same thing I did in the last problem, as we'll see, and then again find the total work to lift the bucket the 100 feet in the air. And just like in the last one, I'm ignoring have a rope of negligible weight. I will say though, if you added a rope and you wanted to add that as part of the weight, well, you could break it into 2 integrals and you could slice the rope and you could scoot the bucket. That's what I would do. But for the purposes of this problem, this is what we're doing. We are not concerned with the rate of the rope. Okay. The picture is very similar. I draw a bucket. It's here at 0, and I want to lift it up here to 100. Except, I don't know. So what changes, I'm still trying to lift it up to 100, is, maybe I'll underline the new stuff, is that the rate at which you're losing water is given as a function of time, really, and the rate that you're lifting it up is given as a function of time. But I want to integrate only with respect to y, okay? So I don't want to write the force function as a function of t. I want to have everything as a function of y, which is the height is my variable. But we can take what's given in the problem and proceed exactly the same as the last problem. We just have to think a little bit. Okay, so let's think about what I'm going to do is in fact convert it to be exactly like the last. So let's think about this variable force. So the weight when y equals 0, exactly the same. We have 2 pounds plus 30 pounds, 32 pounds. Now we have to think about it. I want to use the information that's given to find the weight at y equals 100, and then I can proceed just like the last problem. So let's start with this one here. What's the total time it takes me to get to the top? Well, I need to go 100 feet. This is feet. And if I move 2 feet per second, that says that I move, so I multiply by 1 second every 2 feet, like this. Uh-oh. Let me write it to where it looks kind of like the other one. It would be 1 second every 2 feet, and this would be in seconds per feet. And now you see if you multiply these two, it gives us total number of seconds, which is 50. So it takes me 50 seconds to get to the top. And now I can figure out how many pounds I lose just by multiplying here. So now I lose, maybe I'll put it below. Okay. I was trying to decide where to write it. I lose, well, 0.2 pounds every second. And I have calculated, it takes me 50 seconds to get to the top. So now you see I have lost a total of 50 times 0.2 or 10 pounds. Okay? So now let me go back up over here. So the weight, now I'm in good shape. I'm almost to where we were in the last problem. When y equals 0 is 32 pounds. And this traveling with this constant rate of losing water and this constant rate of lifting, I see that I will have lost 10 pounds of water once I get to the top. So when y is 100, comma, when y is 100, we have 32 minus 10, excuse me, 22 pounds. That's for the water and the bucket. Okay? And now we proceed exactly like we did in the last problem, where, well, you can even see it here. This gives us the slope. You lose 10 pounds over 100 feet. So the slope of my line is negative 1 over 10. Or 10 over 100, 1 over 10. But negative because we're losing. So my force function, f of x, or excuse me, f of y, is, I begin here, and it's linear because it's a constant rate, subtract off losing 10 pounds over 100 feet, or you can do, you have 2 points on the line here and do, let's see, 22 minus 32 divided by 100 over 0, like this, but it's 1 over 10 y. And again, like in the last problem, we can check. If we evaluate this force function at y equals, now this is in terms of height, right? Not in terms of time. At y equals 0, we have 32 pounds. Evaluated at y equals 100, we have 22 pounds. This is my force function, okay? And it's a function of y, the height, which is what I need. And so now I will integrate. So the total work is an integral 0 to 100 of this 32 minus 1 over y, oops, not that, 1 over 10, y dy. And this is not too bad. I'm just about out of space. This is an integral, or it is, excuse me, 32y minus 1 over 20 y squared. This gives us 3200 minus, this is going to be 1 like this, and 1 more over 20. That gives us 3200 minus 500, which is 2700, and this is foot-pounds. I'm sorry, I am out of space. Okay, is that what I got in my notes? Oh, I think so. I just set up the integral and stopped. Okay, I think it's right? Because cancel here, you're left with 500. and then subtract. Okay, it looks good to me. I just set it up and stopped in my notes, but in any case, this is what changes here. We had to write the force function in terms of the height and not the time, and this one was a little bit more involved. Okay, so I have one more type of example I would like to do with the scooting, and that is of a spring. And these are not too bad. These are much more, I will say, straightforward than the leaky bucket problems. So let's discuss this for a few minutes. Let me draw a few pictures of the spring. So we have 3 springs, and they will all have the same, this will be equilibrium here, or I'll say its natural position. I'll write it this way. This is the spring's natural length. And what can happen with a spring? Well, in one case, the spring is sort of at rest. Maybe you have something here attached to the end of the spring, like this. So this is at equilibrium, or when the spring is just at rest. Equilibrium. Okay. Then you can think about compressing the spring and, oh goodness, here, maybe here. And we have the same little block or whatever is on the end of the spring. This is compressed. And the other thing you can do with a spring is stretch it this way. So let me draw a picture of that, and then I will start labeling things, and then we will work some problems. So we have maybe 1, 2, 3, and here. And then here is this little, whatever's at the end of the spring. Maybe it's a block of wood, something like this. And this is stretched. Okay, now, we typically refer to a spring's natural length as x equals 0. And remember when I was starting these work problems and I said I always put my axis based on what it makes sense, and we've done a lot of lifting or pumping that was vertical. Here we have a horizontal axis, so I will label these with x's. Okay. So the natural length is thought to be x equals 0. So if you are at rest or equilibrium, this would be x equals 0. If you are compressed, so this has been here, this, you think about, is compressed this way, you are at some location that's negative, and if you are stretched, so it goes from equilibrium to the end of the spring like this, then you're at some location that is positive. Okay, so these are the different things that can happen with a spring. And then what happens with a spring, there's a few ways to state this, but I will state it this way, is we have something called Hooke's law, which states that the force required to hold a spring, either compressed or stretched, x units from its equilibrium, or I'll just say stretch, I'll take this part off, compressed or stretched, well, that it's not constant. Let me switch markers. From compressed or stretched from its equilibrium is It's not constant, but it is, f of x is k times x, where k is greater than 0 is called the spring constant. Now, there are different ways. This looks like this supposed to be an R. There are different ways to state this, to mention it. I'm talking about the force required to hold a spring, not the force that the spring is doing. If I were to state it that way, I'd put a minus here in front of this. But this is one way to state Hooke's law. The force required to hold a spring stretched, so to hold it here or to hold it here compressed, is of this form. It's f of x is kx, where k is the spring constant, and it depends on the spring. Okay, so, well, this is variable. Okay, so if we need a work, so the force just holds it. Work is force over a distance, right? If we need a work with a variable force, it will be an integral. Okay, so let's do two examples with the spring. Calculate the work. Required to compress a spring 2 meters from its equilibrium when the spring constant is 10. Okay, this is about as straightforward as they come, and then I'll do one that involves a little bit more thought. We'll make sure it's still in focus. Okay, looks good. Well, okay, we know the way I've stated it, we have f of x is 10x. This is the force required to hold a spring, either compressed or stretched. Okay. Now I'm compressing. So this would be, the work would be an integral. We're going from equilibrium to -2 because I am compressing, right? It goes this way of 10x dx. Okay, this is just 5x squared evaluated between 0 and -2. So this is, okay, it's 20. And this would be in joules because this is in metric, right? This is probably the most straightforward of the ones we've done so far. Once we use Hooke's law, that is giving us this part. We just have to integrate 10x. Now, let's do one more spring example that is that we have to think a little bit more on. And this one, pretty much everything was given to us that we put in our integral. It's not always the case that it's that straightforward. So let's do one more. This one I will do with US customary units just to see some differences. So now we have a force of 10 pounds is required to hold a spring stretched stretched 4 inches past its natural length. How much work is required to stretch it 6 inches past its natural length? To stretch it 6 inches past its natural length. Okay, well, let's think about this problem. We are in U.S. customary because we see pounds, but we also see an issue, right? Inches and inches. And we know U.S. customary is not inches pounds or something like this. We must convert. So to work in foot pounds, which is what we need, these are our units of work in U.S. customary. We must convert. 4 inches is 1/3 feet, and 6 inches is a half foot. Okay, very nice. That was step 1. Now you see the difference between this problem and the last, or one difference. We are not told the spring constant. So what do we know here? We know, I'll write what we know maybe in black. We know Hooke's law, which says that the force is kx. And what we want, well, we want the work required to stretch it 6 inches past its natural length. So this would be an integral. We go from 0 to 1/2. My limits of integration are in feet of kx dx. Okay. Now, one final thing. We haven't, right, it looks like we're not going to get an actual number, but I haven't used the fact that I'm handed a force. We have a force of 10 pounds. Is required to hold it stretch, well, this many feet. Okay, so I come back to this. I have a force of 10 pounds. 10 equals K times 1/3. And so I get that the spring constant K is 30. This is step number 1. Well, once I have that, now I'm ready to find the work. I just put in K is 30. So my work is an integral 0 to 1/2 of 30x dx, which is 15x squared evaluated. We have 15 over 4, and this would be in foot pounds like this. This is my total work here in this problem.